This video is produced for those students enrolled in the Cali Maritime EPO 322 Diesel Engineering 2 simulation course. This is the second part of a two-part series on compressed air and cooling water systems. You have a low C-suction and a high C-suction. This simulation is on a ultra-large crude carrier, and at the present time that crude carrier is unloaded and high out of the water. So this green is depicting water level, and you'll note that the high C-suction is out of the water and couldn't be presently used. On a tanker such as this is that you'll change from low suction to high suction depending upon loading condition. In other words, you're on the low suction when the vessel is unloaded and high suction when the vessel is loaded, and you will change these from the one to the other as the loading condition changes at either the discharge or loading port. You have 3 saltwater pumps, 2 large main saltwater pumps that are fed off the main switchboard, and then a very small auxiliary pump that is powered from the emergency switchboard. You also have a fire pump and general service pump coming off of that same C-suction. You have a temperature controller, and it is reading the temperature on the outlet of the saltwater pumps, and it is set for usually about 20 degrees C, and its output is controlling a 3-way valve. The flow from the saltwater pumps goes to one of either redundant saltwater to freshwater coolers. You have a steam turbine condenser. They're only showing one heat exchanger here, but these are for SSDG number 1 and number 2, and they actually have multiple heat exchangers in those rooms, saltwater to freshwater exchangers. Then you also have a distiller, saltwater heat exchanger, and an air conditioning heat exchanger. This is your overboard. This again is your 3-way valve and circulating back to the suction of the pumps. This temperature control system was put in there for Arctic operations so that if you are in a condition where you are in very cold water, it would circulate the water back to the suction of the pump rather than going overboard. Typically on a modern saltwater system, on any vessel, they try to minimize the number of saltwater coolers as much as they can. Saltwater systems are high maintenance and have to be made out of corrosion-resistant materials, which increases the cost to the system. By regulatory mandate, all of your saltwater coolers, there has to be a redundant unit. In other words, if we're talking about either one of these saltwater to freshwater coolers, we would normally only run one of them, and the other is your standby. The same thing on the main saltwater pumps. One of the things I found is when the students are having a problem, say with overheating of a system, they will either put on 2 pumps or they'll put on 2 coolers. I'd never do that in real life. You got to troubleshoot what the problem is. If you think that maybe there's a low flow condition through the pump that's caused by pump wear, you would put the redundant unit on and shut down the primary unit and see if that solves the problem. Then you know that you have to do a pump repair. Similarly, on your freshwater to saltwater coolers, if you think that one of the cooler was plugged up, you would switch over to the other cooler and clean it. So these are the type of conditions that temperature controller was put in for. One of the things of note is most American ships wouldn't have this. But one of the reasons I like to talk about this is as soon as I saw that temperature controller, I was wondering what that was there for. In other words, to put in a temperature controller 3-way valve, you're talking quite a bit of money, probably $20,000. Always when you see a system like that, you want to dig into it and find why it's there. So this is the type of conditions depicted down in this lower right hand one where we've got ice and a lot of fresh water and ice forming outside the ship, what can happen with you is that a sheet of ice can form over the top of that intake and then cause a low flow condition, and you start overheating all your equipment aboard the vessel. So to prevent that, by recirculating that water back to the suction of the pump, and whenever it is lower than 20 degrees C, this would help to prevent the ice formation on the sea chest itself. Quite a majority of the heat exchangers on modern vessels tend to be plate type heat exchangers. You can also, by the way, have tube and shell. But I'm going to talk about the plate type exchangers for a little bit here. And these are sized appropriate for this freshwater to saltwater cooler. You also have seen them on the Bear. They're pretty popular because they're easy to disassemble and clean. One thing of note, whenever you are going to do this procedure, always measure the distance between the backing plates all the way on both sides around its circumference and jog down that dimension. One thing that can be a problem with these coolers is once you've taken it apart and cleaned each one of those plates and you're putting it back together, you want to squeeze the plates back to that dimension that as where you took it apart. If they're too loose, they'll leak. If you tighten them too much, you tend to squeeze those gaskets, it'll leak also. So always put it back as you found it. And again, you would normally run only one of these coolers at a time. The only exception that I know of is I have been in the Red Sea and the Persian Gulf where you're 95 degree saltwater temperature. That was such an overload with that hot salt water that we ended up running two of these coolers. But typically you would never really do that other than that type of an extreme. The reason being, if you're running two coolers all the time and then you find that you don't have enough heat exchange, you've got nowhere to go. You'd have to shut the plant down to actually work on it. In the Kongsberg simulator, in many instances, both on the freshwater side and on the saltwater side, you have three pumps. You basically have two main saltwater pumps that are redundant, and you would never typically run both of those pumps. Again, if you were troubleshooting and you thought that one of these pumps had a low flow rate, what you would do is you would put the redundant unit on or the standby unit and shut the one that you think has a low flow rate down and see if that solves the problem. This is an example what be of your auxiliary pump. Your auxiliary pump is supplied with power off only from the emergency board. So the main pumps are off the main switchboard. Your auxiliary cooling water pump is off the emergency board. And when you're starting up this plant, your main saltwater pumps will not be available to you, only this auxiliary. And it is sized appropriate to the heat load of this plant in port. A little bit on the automation. This Power Chief pump compressor control is controlling the standby status of the pump. You are also putting in the lead pump. And typically on most vessels, let's say, or a common way of managing this is you would be running all number one pumps 1 month and number two pumps the next one, so that you are getting equal wear on the pumps as that ship is getting older. But they were also, this automation will automatically start up the standby pump in case of a casualty. In other words, let's say your saltwater pump, the one on the line breaks its coupling. The pressure on the pump discharge would drop. That would be sensed by a pressure switch. And then the automation would sense that pressure drop, automatically start up the redundant unit. It will also sound an alarm over the alarm system so that your standby engineer, whoever's got the duty, will be notified that there has been a change in the plant status, and you would have to go down there and check out what the problem is. When you got down there, both of these pumps would be running. So hopefully you know which pump was on the line before the casualty. You would shut that down, see if your pressure's okay, everything's copacetic, then try to put it back on the line and try to determine what the problem is. So all of your vital pumps have to have an automatic control system that will automatically switch over in case of a casualty, and also that automation has to notify the operating engineers that there has been a change in the plant. On the air compressors, you typically have a master, or the way that it's termed on the Bear is a lead lag. Since you have multiple air compressors supplying high pressure air, if you're out at sea and air consumption is quite low, only one of these compressors would start up. As the pressure dropped down, it would start and fill the bottle back up and then automatically stop. But in a maneuvering situation, your air usage is very high. Then what would happen is the master would come on the line, start supplying its full rate. But because you're using so much air, it would drop down below that start pressure and the redundant unit would start up. So this power chief, this is your compressor automation to control the standby and alarm, standby status of the pumps and the alarms. On temperature control, the most common temperature control used on modern vessels is to use a three-way valve. What that does is that means that the water, in this case going to this cooler, is the water can either go to the cooler to bring the temperature down, or it can bypass the cooler, right? So what's going on is if the temperature is high and you want to go to the automation, the temperature controller wants to go at a high cooling rate, the water will flow into the cooler and out. But if the temperature is brought down too low, it can bypass the cooler entirely and to maintain that temperature or to raise the temperature up. And that's the most common methodology used today for the control. Then you have to have a temperature controller, and you have to have a control valve. Now, in this example, we're going to use the Bear jacket water system. You have in this blue unit here that is a Rosemont temperature transmitter that is sending a signal to a GE Fanuc programmable logic controller. That interprets that information and sends an appropriate output signal that is changed in an I/P from a current to a pneumatic pressure. That pressure is sent to a three-way pneumatic mixing valve. That mixing valve will swing so to control flow to the cooler or bypass the cooler to maintain temperature. This is the Kongsberg freshwater cooling system, and it uses a fairly common among the Europeans system, which combines both the freshwater cooling and the jacket water. Also, the terminology used in the simulator, which is much more common than freshwater and jacket water in the international use vessels. It uses low temperature freshwater cooling and high temperature freshwater cooling. Low temperature is what you're used to on the Bear is freshwater cooling. High temperature freshwater is the jacket water. And it looks a little bit confusing, but let me explain it to you and you'll see that it's not all that bad. All right, these three pumps are for low temperature freshwater cooling. You have an auxiliary, which is a small pump, and two main pumps. They discharge into a common line that is going to all of your freshwater cooling services throughout the ship. And then as it goes through these coolers, it travels back up through this bypass valve, back into whatever cooler is lined up, through a mixing valve, and then that is your cooling circuit. Now, the temperature controller here is going to be set for 30 C. It is looking at the temperature to the inlet to the pumps, and it is controlling this three-way mixing valve, and it can either bypass the coolers to bring the temperature up or send the water through the cooler to bring the temperature down. On the high temperature system, it has, again, 3 pumps, an auxiliary and 2 main. It discharges water to the main engine. You have included a high temp fresh water heater. This heat exchanger uses steam to maintain the temperature of the jacket water when the engine is in port. Normal jacket water temperature at the outlet of the engine is 80 degrees C. So in port, you're going to have this heat exchanger and flow through it to try to maintain that temperature up close to normal. When you're bringing the plant up on the line, realize that the engine manufacturer says that this engine has to be at least 50 degrees C prior to startup. By keeping that engine hot all the time, you prevent corrosion in the engine, and you also make it easier for the engine to start. A cold engine, the incoming air into the cylinders, with the heat of compression, there may not be enough temperature to ignite the fuel. So you have a temperature controller here, and that is looking at the temperature at the outlet of the main engine, and it is sending a signal to this three-way mixing valve. If the temperature is low, the flow through the system is through the pumps, into the main engine, out of the main engine, and then the three-way mixing valve is going to just circulate the water in this fashion. If it is trying to bring the temperature down, the three-way valve will shift, and water from the low-temperature freshwater cooling system will flow through the pumps, through the engine, and then it goes back through the cooler and through the system like this. Okay, so this three-way valve is controlling the temperature of the main engine. Now, the best way to really understand this work is pick lesson 6, and one of the things what you can do is put this controller in manual and start making changes and looking at your different flow rates, and if you have any confusion, that should help with that. The other thing on this line is you have the high temperature freshwater cooling going through the evaporator. Now, typically on a large engine, it's only a portion of the jacket water because the evaporators are much smaller in size than what would be needed for that full flow. So in many cases, only a portion of the cooling water will flow through that. One thing I want to note and talk about a little bit with you, though, is the fact that when you, as a cadet or as a third, you're going to be asked to switch these valves over. Usually what happens is you put the valve, once you get out of port, and the main engine is coming up on full line, then you will switch this. Just remember always to open the cooling water to the evaporator prior to closing the bypass, or you can shut water off to the engine while it's under load. So the next subject we'll talk about a little bit is the expansion tank and also on the high point vents. This is a vent from the high point on the main engine. Typically these would come off one off each cover. The reason for a high point vent is to prevent the accumulation of air in high spots. Get the air pockets, which would impede heat transfer and could overheat the engine. So one of the things I would like you to think about is down even to the minutia of these small vents. One of the things that happens when you pull a cover on one of these engines as you're doing maintenance, they typically have a quick disconnect and there's a little valve there, so when you pull the cover off, you don't lose water. If you were to take and put the cover back on, finish your maintenance, forget to open that vent up, then as you're running that engine, that cover can overheat and cause a crack. So It is important that you understand that on these types of systems, high points on all your heat exchangers, and in this case the main engine, you will have vents to prevent the formation of these air pockets, and typically those go up to the expansion tank. Now, I want you to also note that the main engine here on the high temperature fresh water is separate from your auxiliary diesel generators, and this is common. The high temperature system for the main engine is separate from the generators, and we'll talk about, as we talk about the expansion tank, I'll discuss the reasons for that. And then here's your expansion tank, and in this system you only have one expansion tank for both of these low temperature and high temperature fresh cooling water systems. So we're going to finish up with the discussion of the expansion tank. Out of sight, out of mind. What is an expansion tank there for, and what is important about it, and why should you check it every day? Well, an expansion tank are mounted high up in the engine room. They're there to give a pressure head to the suction of the pump. They are also serve as, the name gives you, an expansion tank. As the system cools down or heats up, the water in the tank will expand or contract. Usually you keep the expansion tanks about 3/4 full. If you were to add too much water while the vessel's in port and that expansion tank is fairly cold, then as you start up the main engine and that water heats up, you'll overflow the tank. So it allows for expansion. It serves as a reservoir of fluid. And typically you only should be adding water to that expansion tank at a very slow rate because of any evaporation, which is usually pretty small. Most chief engineers will have a clipboard or some method of providing the assistant engineers a way of recording each time that you add water to the system and how much. The reason you're doing that is so that if there's any leakage in the system, that you will have a way of determining this. If you are leaking, you first do an external exam of all your pumps and valves and fittings. External leaks, if they're minor, are really not that large a problem, but of course as part of a normal maintenance procedure you're going to take care of them as soon as possible. But if you can't find any external leaks, then you have internal leaks. And internal leaks, where you have cooling water leaking inside the engine, can be really detrimental for corrosion and other problems that it will create. Internal leakage can be a little bit difficult to determine. If you have conventional purifiers like we have on the Bear, you can look at your purifier heavy phase discharge. And you should never see water coming out on a continuous basis. So your purifier would remove any water that was coming into the crankcase, and it would remove it from the oil, and you would see water coming out of the heavy phase, and that would tip you off that there is a problem. Newer vessels actually are operating their purifiers as a clarifier, and you would not have this trigger that you would notice. So in that case, you may pick up the water through your oil testing procedures. In that case, they will see the chemicals from the cooling water system will show up in the oil, and they can warn you that you have a leak, or you may see internal corrosion and those types of problems. The last subject that we'll talk on this is cracked liners and cracked covers. If you were ever to walk up to one of these expansion tanks and you're looking into the sight glass and you see rapid bubbling like it's boiling, walk over to the vent and then kind of take a whiff of the vapor coming out of the vent. If you start hacking and coughing, that's exhaust gas. And that exhaust gas is getting into the cooling water system through a cracked liner or a cracked cover. In some engines, but there's not many marine engines out there that can do it. The Enterprise is one. It can be a leaking head gasket. So the Enterprise, you can also have a leaking head gasket, and that would allow the exhaust gases to get into the system. But most engines, it's a crack liner, crack cover. And what's going on is those high pressure gases are moving through the crack and getting into the cooling water system. This is very detrimental, and this can cause an engine to seize very, very quickly. If you ever note this, that you have to immediately notify the chief engineer or the first, whoever there's the policy on that vessel. And you have to determine which engine is leaking. This is the reason that the main engine high temperature freshwater system is typically kept separate of the auxiliaries so that you know immediately if it's the main. Now, if it's an auxiliary, you can always go and put another generator on the line and take the one that is on the line off to see if that solves the problem. But again, this is a primary way that you can determine when the engine's running, if you see gases coming into that expansion tank in significant quantities, it's most likely crack liner, crack cover. All right, that concludes this presentation, and thank you for listening.